Let's solve USACO Silver Problem 1 2018 convention. So we have a list of cows that want to go to a convention. Now Farmer John has arranged M number of buses with C capacity for N number of cows. He wants these cows to get to the convention in an efficient amount of time. So he's trying to reduce the maximum waiting time using the buses and capacity constraints. Now we're given input file where the first line is N, M, and C. So this is the first line, N, M, and C, where N represents number of cows, M represents number of buses, and C represents capacity of bus. Just for the sake of this simple sample input, we're going to use these variable numbers. So 6, 3, and 2. That's our first line that we need to gather to solve the problem later. Now for the second line, we have the list of cow arrivals. I'm going to go ahead and call this arrivals. So it says cow 1 arrives at time 1, cow 2 arrives at time 1, cow 3 arrives at time 10, and so on. Now, if we want to solve this problem easily, we need to sort cow arrival times to make it easier to group cows that arrive close together. Now, these list of cow arrivals is going to look like this. 1, 1, 3, 4, 10, and 14. Now we gather all the information, let's start thinking about how to solve this problem of efficiency, right? We're essentially finding the min-max waiting time. Now we should consider this constraint of M times C is equal to or greater than N. This really complicates things. Most of you might think about just finding the optimal group by grabbing the length of N arrivals and then dividing it by the capacity, like so. 1, 1, 3, 4, and 10, 14. Then iterating through these groups and finding the max time. And that will give you the min-max time. However, this won't always work simply because of this constraint of M times C is greater than or equal to N. We might have more buses than cows, and the capacity might be more than N as well. It could really mess things up. So it's not a simple mathematical problem. There is multiple solutions for this. There are too many factors to consider. Now, you may think about using a certain arrival time and then slowly increment it up until you get a max waiting time that satisfies the constraints. However, that is the brute force approach of O of N squared, and it's really slow. You're checking all the possible combinations in a very slow manner. However, let's think about it in a different way of solving this. So instead, we are going to go ahead and binary search multiple valid max waiting time solutions. We got to do this under buses and bus capacity constraints. So now that we're thinking about binary search, we have to think about the range of possible answers we can get. There's a lot of factors to consider. However, there's a way to narrow down these answers. So at the bare minimum, there's no waiting time of 0. That means all our cows in our group or groups arrive at the same time. That is 0. That means min-max can be 0. Min-max waiting time can be 0. Now this is the harder part. Technically up here, it's up to 10 to the power of 9, right? That's a lot of answers to search though. We could probably narrow this down even further. Let's think about worst case scenario. We only have one bus, right? And it has the capacity to take every cow. That waiting time is going to be the last element or the last cow minus the first cow arrival time. So this significantly cuts it down from 0 to last cow time arrival minus first cow time arrival. Now let's try to do the sample input that we figured out earlier, where we have an arrivals of 1, 1, 3, 4, 10, and 14, and these NMC values. So this range is going to look like 0 less than or equal to min max waiting time less than or equal to 14 minus 1, right? So that's going to be 13. So in total, we have 14 possible solutions. And since we're binary searching multiple valid max waiting time solutions, we want to converge at the minimum value for maximum waiting time. So let's think about how that's going to look like. So let's say we have a list of all the possible solutions, right? It's going to be the length of 14, right? So earlier we were already given the solution that the sample input is going to return 4 for the min-max waiting time. So our given answer was 4 down here. And for right now, we'll just work with that. So that means everything before 4 was not a valid waiting time, a valid max waiting time specifically. So that's going to look like false, 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 and false. It's going to look like 0, 1, 2, 3 did not work. And because we're looking for minimum maximum time, it converges here at this true and false. Specifically, it's going to be true on min max waiting time of 4. See, notice how this is at index 4. So that means everything after that is true. We're just giving it the valid max waiting time to increase, and that will still satisfy those conditions. So this keeps on being true all the way to index 13. So that's our list of solutions, right? Now, let's kind of see how the code is going to look like for the binary search. So we have low that starts at 0, indicated here, and the high that starts at 13. So the binary search algorithm looks something like this. While low is less than high, that means we want to converge at some point. We're going to constantly recalculate mid, the midpoint specifically, or the mid number. We want to check if the mid value is not a valid waiting time. So it's going to look something like this. Not valid waiting function. We're plugging in the mid value. So if it's not a valid waiting time, we want to go ahead and get rid of the left-hand side. Constantly do this, while else we save the answer and we should eventually converge to this true value of 4, which can be represented as high and would be equal to 4. Now, I used a function here, valid waiting, and I plugged in mid. So let's talk about how that function is going to look like, right? Now we have a function that we're going to name valid waiting. We're going to input an integer max wait. Then we're going to output a Boolean. And that's what we're feeding our binary search algorithm. And I want to modify this. So I'm saying that I'm feeding mid to the max wait input. Now this code will do a lot of things. We're first binary searching multiple valid max waiting time solutions using the valid waiting function. And then we're narrowing it down at a convergence point of high or 4 to get the min max waiting time. Now this search is O of log n. So to make this efficient, I have to make this O of n or smaller. We want to make this algorithm faster than O of n squared, the brute force approach. So that means I have to iterate through arrivals list once, right? So how we're going to do that? So first we have to start with a couple of variables like buses, and then cal left indexed and cal right indexed. Now you can imagine this as a while loop here. And then we're going to constantly use a 2 pointers or a sliding window. It's kind of a hybrid of both technique to check if it's a valid waiting time given constraints of C and M. So when I'm iterating, I want to check first, if first cal in bus, we want to increment bus's counter, which is here. So how can we check if it's the first cal in the bus? We manipulate these indexes of left and right for cal. So if they're overlapping, that means it is the first cal in the bus. Then we're going to use a bunch of if-else statements. So the next set of if-else statements is first going to start with if bus waiting time out of set range, we update cal left index to cal right index. So what do I mean by if bus waiting time out of set range? We basically subtract this right index element minus this left index element, and then check it if it's greater than max wait time. So it will look something like this. Then we update the cal left index to cal right index. That means there's overlapping indexes. When we loop back around into this if statement, which will also cause to increment the bus counter. Now let's think of another case where the capacity is reached. So else if bus capacity reached with new placement, not after, but right before, we want to go ahead and increment cal right index. So we can proceed iterating through the list because the previous bus group was valid, or the current bus group. Now after we incremented the right index, we go ahead and overlap indexes to move on to next bus. Then our last else is else cal time is valid or bus placement. So let's say it's a second cal placement out of 3 spaces for a bus. We just go ahead and increment the cal right index to indicate we were able to place this cow in the bus given the M and C constraints. Now we continued doing this until we iterated through the entire arrivals list. After that, we go ahead and return buses is less than or equal to M. So this is basically an if-else statement in here. So if the buses are less than or equal to M, it returns true, else it is false. Now let's run through this function. Let's say I'm given a max weight of 4, right? We go ahead and start this while loop. So if the first cow in bus overlapping indexes, they are overlapping because we have cow left index is equal to 0 and right index is equal to 0. So the bus's counter goes up by 1, right? So let's move on to the next if statement. So if bus waiting time out of range, and I just noticed I made a small error. This one's different. It should just be right element minus left element using cal right index and cal left index. So we check this condition. So 1 minus 1 is equal to 0. So this is 0 right now. Then check if it's greater than max waiting time of 4. It is not. So we skip this if statement. So let's move on to the else if. Else if bus capacity reached with new placement, we have a capacity of 2. This is the first cal, so we skip this. We increment cal right index. So now this is 0 and 1, indicating we're looking at 2 items in the bus. We skip this if statement, we skip this if statement, we check this. So if else if bus capacity C reached with new placement, this is a new placement by the way, we increment the right cal index. So that's 2 now, and overlap the indexes to move on to the next buses. So left index gets incremented to 2, and then we overlap yet again to increment a new bus. Then check this if statement, still works. Check this else if statement. It's the first count on the second bus, so we skip it. Else we increment right index 3 and proceed onto this else if statement where we increment right index of 4 and overlap it by 4, then put buses to 3, and so on until we reach a right index of 0, 1, 2, 3, 4, 5, and 5. We break out of the loop with 3 buses, and it should return true for this high value of 4. We constantly do this with multiple valid max waiting time solutions until we converge to this first true solution, which means the answer of high at the end of the convergence is equal to 4, the min-max waiting time. Okay, so let's solve USACO Silver Problem 1 2018 convention in Python. Now, I've gone ahead and made the sample input, so let's start off with that. So we're going to read the input file. Now, in the prompt, we learned that the first line, n is equal to number of cows. That's the first number. Second number is m, which is represented as number of buses, and c, which is represented as capacity of bus is. So we have 3 variables on the first line, and we're going to map them as integers. Next, we have a second line, and that's going to be practically it. The second line is cal arrival times. We're going to store that in a arrivals array list, and they are a list of integers. Now we're going to go ahead and print them out, make sure we have them. We have 6, 3, 2, and then the second line. Great. Now we need to sort cal arrival times if we want to solve this problem, because we're trying to group cows that arrive close together to fit them on a bus to get to the convention on time. In short, we're efficiently scheduling buses for our cows to get to the convention as soon as possible. We're solving for the maximum waiting time. So we're going to go ahead and sort it by using the sort function built into Python. Now we go ahead and try to binary search for min-max waiting time. And earlier we discussed why binary search is the best approach to this problem. There's a lot of variables to consider, specifically how m times c is greater than or equal to n, meaning there's multiple answers to this depending on what is c and what is m. So let's figure out the range of answers we will probably get. So at the very least, min-max waiting time is 0, and at most, it is arrivals last element minus arrivals first element in the case where we only have 1 bus per se. This makes it easy to identify what should be our low, what should be our high answers for binary search. I'm going to use -1 to represent the last element of arrivals and proceed to make the binary search algorithm. So we're constantly updating mid, and then we're running two if-else statements. So I'm going to say if not valid wait time. I'm going to represent this as a function to easily understand my code, where we have an input of max wait. We'll plug in mid to that. So if this mid value is not a valid waiting time, max waiting time, we go ahead and get rid of the left-hand side of our solutions from low to high by going ahead and setting low to mid +1. Else, we save our solution by updating high to mid. This gets rid of possible solutions, but that are not the minimum maximum waiting time. That means it will eventually converge to high, essentially right here. Now, the reason why we use binary search is to cut down the time of finding this solution from O of n squared to O of n log n. So far, we have O of log n. Now, we need to make an algorithm for the function valid waiting. So let's start off by defining valid waiting. And to make this efficient, I can only iterate through the arrivals array once, or I can only iterate in O of n time if I want to make this efficient. So I need 3 variables to make this work. Buses, cal left index, and cal right index. Imagine this left index represents the cal arrival time, the first cal arrival time, and then this right index represents the last cal arrival time. So we're going to go ahead and iterate using a while loop, and using our cal right index is less than n. That's our most current, our highest index we are checking in the arrivals array. Now this is the portion I was talking about earlier about a two pointers / sliding window approach. We have a lot of if-else statements we need to check and constantly change values for buses and cal left index and cal right index. So let's start off with the first if statement. So if first cal in bus, so that means we have overlapping indexes. We want to go ahead and increment the bus counter. Then we move on to a bunch of other if-else statements. So let's start with the first if statement. If bus waiting time out of range, so this if statement is going to look like this. If arrivals at our last cal minus arrivals of our first cal is greater than this set max wait value, that means we need to go ahead and put them on another bus. Now this means if we continue doing this, it is technically possible to increment buses higher than m, which breaks the m buses constraints, but we'll deal with that later in the return statement. So let's move on. So else if bus capacity C reached with new placement, we can represent this as else if the last cal index minus the first cal index is equal to C. However, we need to modify this to add a 1 to include the last cal element, and we're going to go ahead and update indexes to move on to next bus. These are 2 steps though. We need to increment our right index to show we're moving on to another cal, and then update cal left index to cal right index to later increment the bus counter when we loop back around. Now we have this last else statement. So this means else cal time is valid for bus placement. And we just increment the cal right index. Now this will continue on until it is equal to n or greater, and then we go ahead and return if the amount of buses we counted was less than or greater than m. This is how we check if this is a valid max wait time. And we were able to check this by checking if it meets the buses m and bus capacity C constraints. We do this on multiple answers until we converge to a minimum maximum waiting time. This takes O of n time, simply because we are not resetting our indexes, we're constantly incrementing by 1 and O of n time. So O of n time times log n is n log n. So that time complexity is going to be n log n up here. And our memory complexity is O of n, where we stored arrivals into an array. You can argue it's O of 1, either or. Now let's go ahead and write our converged answer to our input file. So I need to modify this down here. Let's go ahead and run it. We got 4. That is the answer we were looking for. So let's zoom out and show my final answer. Notice we also had a sort, which is n log n time. However, n log n plus n log n is still n log n. So now we're going to move on to the web page. So we're on the web page now. We're going to go ahead and select Python 3.6.9 and then choose the file. We chose test.py where it coded. We submit. And we were able to pass all our test cases. So that completes our Python solution. Okay, so let's solve convention in C++ now. So I went ahead and created the input file we were given, 632, and the second line of arrivals. Now, let's go ahead and interpret that information. First, we need to go ahead and include IOStream. I'm not going to use bits std C++, just so I can learn where these algorithms, these methods, these functions come from. Next, we have to include a vector because we're going to grab a vector from the second line. I'll discuss that in a bit. So let's start off by opening the input file. We can open the input file by using free open convention.input file. We're going to go ahead and read it. And let's interpret the data. So in the first line, we discussed how the first integer value is n, which is represented as num of cows. M is the second integer value, which is represented as m of buses. M number of buses. C is represented as bus capacity for each bus. So let's go ahead and grab those values, n, m, and c. Now I'm going to make these global values, global integer variables specifically. So int n, m, c. Next, we're going to go ahead and grab second line, which discusses arrival time of all cows. And we want to append these values or store these values inside a arrivals vector integer variable. So I'm going to say vector int arrivals up here. Now, if I said n is number of cows, that means there should be 6 cows here for n is equal to 6, and it does work out. So let's actually initialize our arrivals array to size of n. Then we go ahead and plug those values in. So we're going to iterate through each cow in that single line. Then let's go ahead and test if we grab the values correctly. So let's print these values out. We got n is equal to 6, m is equal to 3, c is equal to 2, and then the vector list. Great. That works. Let's get rid of these print statements. And I forgot to put this open input file comment up here. Now, what the problem is discussing is Farmer John is trying to get these cows to a convention with M number of buses with C bus capacity. Now, he's trying to get these cows there as fast as possible. So our task is to find the min-max waiting time. Essentially, we make an algorithm to find the most efficient bus groups, then find the max arrival time for one of those groups, at least for one of those groups. Now, there's a lot of constraints to consider. Actually, m times c is greater than or equal to n. This really messes things up. It's not a simple math problem. At this point, it really depends what m and c is. So let's create a binary search to find the min-max waiting time by testing out certain max wait values and seeing if they are valid or not. So binary search min-max waiting time. So we need to find what is our lowest answer and what is our highest answer. So our lowest is, imagine that we have one bus and all the cows arrive at the same time. There's 0 waiting time there. Therefore, the lowest possible answer is 0 for min-max waiting time. The maximum value is our latest cow arrival minus first cow arrival time. Now, what does that look like? We grab low, which is an integer. We grab high as arrivals, and -1 that represents latest cow arrival minus first cow arrival, which is arrivals 0 index. Now we can go ahead and create this binary search algorithm where we're constantly recalculating mid as we change low and high in our if-else statements. So let's figure out what should go into if and else conditions. So I talked about a valid waiting time. So what if we made a function to make this look cleaner? Specifically, valid waiting as a function that checks mid. Now let's say if this mid value as a max waiting time is not valid, we go ahead and get rid of the left-hand side of the possible answers. Else, we save our answer at mid and slowly converge to the minimum maximum waiting time. And that's going to look something like this, where we open our convention.output file, and we're going to go ahead and write high, our last recorded valid answer. C out low or high is written into the output file. Now, So far, this is easy to understand, but we still need the underlying algorithm to check if a max waiting time is valid or not. In this instance here, I am returning a false or a true. So we need to create a function called valid waiting that outputs a boolean and takes in a max waiting input. So let's create that. Let me just move this down. Let's create a comment discussing what this function does. So we check if max waiting time is valid under buses M and bus capacity C constraints. Now this algorithm has to be an O of n time to be faster than the other approach of brute force checking every combination and slowly incrementing to a valid waiting time. That's a min-max waiting time. Because so far we have O of a log n time complexity. So therefore, if I want n log n time complexity, I need to iterate through arrivals vector once in O of n time. Now we haven't really used the arrivals vector, and I actually forgot to do one thing. So in order to group pairs easily, we should sort. We're going to use the sort function from algorithms library. We need to include that here. And now we're ready to make this valid waiting function. So now that we're sorted, we can go ahead and iterate through arrivals, basically using a 2 pointers / sliding window approach, where the left pointer or the left index and the right index represents the first cow and the last cow we are observing in each bus placement. So we need to create those variables first. So I'm going to create a buses counter named just buses, initialize it as 0, and then cow right index and the cow left index. Now, cow right index means this is the last cow placement in the bus, and left index means the first cow placement in the bus. Now we're going to use a while loop where the condition means while we iterate through the arrivals array in the index range of n, we're going to use a bunch of if-else statements to increment buses and change the value for our indexes. So let's start off with the first if statement. So if first cow in bus, that means we're overlapping indexes, we increment the bus counter. So let's use if cow left index is equal to cow right index, we increment buses. Now we're going to use a sequential if-else conditions. Our first one's going to be if bus waiting time out of range. It's going to look like this, where we grab arrivals array and we grab the last cow placement in the bus minus the first cow placement in the bus is greater than max wait. We need to reset our indexes. We need to update previous index to current index to move to the next bus. It's going to look like this. We want them to overlap to increment the bus counter later when we loop back around. Now let's move on to our next else if statement. So else if bus capacity C reached with new placement, we can represent it as so, where cow right index can be included minus cow left index is equal to C. That represents how many cows have been placed inside of the current bus. We want to go ahead and update indexes to move onto next bus. So let's move on to the next cow by incrementing cow right index and then overlap them on top of each other. So when we loop back around, we increment the bus counter. And then our last else statement is else cow time is valid for bus placement. We don't have to worry about anything else. So we increment cow right index. Now, this will eventually reach n or pass it. Therefore, it is possible to have more buses than the m constraint. I didn't use an if statement for that inside of the while loop, but we can use it outside of it. We can return buses less than or equal to m. So if buses is less than or equal to m, it returns true, else it returns false, just like these array of solutions down here. We check if the max waiting time is valid under these constraints of C and M. So let me just zoom out and check for any issues. Forgot a semicolon here. And let's go ahead and run our problem solution. We got a result of 4. That is exactly what we want. Therefore, this is our final solution. And I want to discuss how this is n log n up here. So first off, we iterated through our second line in O of n time. Then we sorted an n log n. So that's our biggest factor so far. Then we binary searched an n log n because of this valid waiting function up here that iterates through an O of n. So n log n plus n log n is equal to n log n in big O notation. Now the memory complexity is O of n simply because we stored all the cows inside the arrivals vector. So that concludes our solution for C++. We're going to move on to the web page to see if we got it right. So now we're on the web page. We're going to select C++17. We're going to choose the file. I selected test C++. We're going to submit. And our solution works. So that concludes our C++ solution. Okay, so let's solve the convention problem in Java now. Now, I created the input file here, and we should start off with that. So we've created a main method for Java to run our actual code. However, we need to include something here. We need to include a throws IO exception for input output. That will include a library for us. And let's just include everything from java.io. And let's include everything from java.util for later use. So we're going to go ahead and open the input file. We're going to use a buffer reader and a file reader. The name of the input file is convention.input. I'm going to go ahead and read the first line using a string tokenizer and input.readLine function. So the first line is told in our description where the first integer is n and n is equal to num of cows. Second integer is m, represented as num of buses. Third integer is c, which is bus capacity for each bus. So let's go ahead and grab those values by using a parse integer function along with st.nextToken. Now later on, I'm going to create a method and I want to use an instance variables inside our class solution so we can use it across all the methods. So we're going to say static int n, m, and c. Now let's move on to the second line where it represents all cow arrival times. We need to go ahead and move on to the next line by using a new string tokenizer and including the note line. So we grab arrivals. This is where we're going to store our array. Now we should start off by declaring it outside of our main method as static int arrivals. Then here in this line 21, we're going to go ahead and say it is the size of n. Now we can feed in values into our arrivals array. So using a for loop, we're going to iterate through each cow up to n. Then we could go ahead and close the input file. So let's talk about what the problem is asking. Farmer John wants to get all these cows to a convention in the fastest time possible in the arrivals vector or arrivals array. So these are the times our cows arrive and are ready to go on a bus. Now he wants to find out what is the min-max waiting time. So that what that means is we got to efficiently schedule our buses for our cows to minimize waiting time. Now, there are a lot of constraints to think about where m times c is greater than n, and this makes it more complex, a lot more factors to consider. Therefore, we should take a different approach where we first go ahead and sort our group of cows to pair the buses easily. Now, we should binary search min-max waiting time. So let's think about the range of answers we can have. So the smallest possible answer is 0. That means all the cows arrived at the same time. And the biggest possible answer is last cow time arrival minus first cow time arrival. We can represent that as low is equal to 0, which is the lowest possible answer, and high is equal to our sorted arrivals at n minus 1 minus the first cow arrival. That's how we can represent the highest possible answer in our solutions instead of 10 to the power of 9. This saves us a lot of time. So we can go ahead and start our binary search by using a while condition of low is less than high, then constantly changing mid inside of our binary search. We're going to use low plus high is minus high minus low divided by 2. So our mid integer fits inside our int data type. So let's move down and continue. So I can make this code look a lot cleaner by using just an if and an else. And inside of this if condition, we use a function that we'll later figure out. So this function is just going to check if this mid input representing as max waiting time is valid or not. So we're going to say if not valid waiting for mid, we go ahead and ignore the left-hand side of our answers. Else we found an answer, but we want to slowly converge to a minimum value for max waiting time. Therefore, after our binary search, that means we should write our converged answer high And it's going to look like this, where we have a bunch of falses, then eventually a true. That's going to be our high that it converges to. Then a bunch of trues until we reach high. This represents our min-max arrival time answer. So we can go ahead and write our high to our output file. So we're going to print the line to our output file, high, then we go ahead and close our output file. Now we have to figure out our underlying algorithm to check if a max waiting time is valid. That means we're going to check a certain waiting time and see how many buses it takes. If those buses are less than or equal to the M constraint, we return true, else we return false. So let's start writing our valid waiting function. And I'm actually going to write this down here at the bottom. Private static boolean, we're going to return a boolean, valid waiting, and our input is max wait. So yet again, let's discuss what this function does. So check if max waiting time is valid under buses, M, and bus capacity, C, constraints. Now, we want to be faster than a brute force approach of O of n squared. That means I have to figure out a way to test this out in O of n time, so I can make an O of n log n algorithm with our binary search. That means I need to use a 2 pointers / sliding window algorithm approach. So we need a couple of variables to make that work. We're going to use buses counter, a cal right index, and a cal left index. These are our 2 pointers or our sliding window range. Now we're going to go ahead and iterate through the arrivals array with the following condition. So our cal right index signifies the index of our last cal we place in our bus, while cal left index represents the first cal we place in our bus. We'll see how that works in a bit. So if our first cal in bus, so this means we have overlapping indexes, we're going to go ahead and increment our buses counter. Now we're going to have a long list of if-else blocks of code, so we can loop back around to this if statement afterward. So let's start off with if bus waiting time out of range. What does that mean? So we want to see if the waiting time exceeds our max wait time. So we grab our right element using cal right index, representing our last cal placed in the bus, and our cal left index as our first cal placed in the bus, and subtract them, then compare it with max wait. So if this value is bigger than max wait, that means we need to reset our indexes to move on to the next bus. Now our next else if is else if bus capacity of C reached with new placement of the bus, we have to go ahead and update our indexes and then move to the next bus. So that looks like so. Else if cal right index, we got to include the cal right index by adding a 1 minus cal left index is equal to C. So these indexes signify the range or the amount of cals we fitted on one bus. So after we check this condition, we go ahead and increment cal right index to move on to the next cal, and then change our cal left index to our cal right index so they can overlap and increment buses on the next loop. So we have one else condition left. So else cal time is valid for bus placement. It's just an else statement, and we go ahead and increment our cal right index to move on to the next cal. Now this will continue on until we break out of the while loop, and as I earlier said, it is possible to use more than m buses in this function. However, we want to check that at the end where we're returning by comparing buses is less than or equal to m. So if bus is greater than m, it's going to return false, else it will return true. And we'll run this inside of our binary search algorithm, continuously checking different max wait answers until we converge to this high value, which represents our minimum max arrival time. So let me just zoom out and check for any errors. Let's run this, and our solution worked. Now let's talk about the time and space complexity. We iterated through our arrivals integer values in O of n time here. Then we sorted in n log n, so that's the biggest factor so far. Then we search in log n. However, inside our valid waiting function, we use a time complexity of O of n. So n log n plus n log n. That simplifies to n log n in big O notation. Our memory complexity is just going to be the size of arrivals, which is just n here. And that concludes our answer for Java. We're going to go ahead and move on to the web page to test out our code. So now we're on the web page. We're going to select Java, then we're going to choose our file. I select the solution.java for the code I wrote, submit. And we passed all our test cases, making our Java solution correct. So that concludes our Java solution. Thank you.